Hello. Today's topic is to create a kinetic toy which is called switch pitch ball, like this one. And I would like to mimic this ball's transformation using Houdini, and it works like this. So if I rotate this ball, it changes its faces using really smart structures inside. And if I do it slowly, it transforms like this, from purple to blue and blue to purple, like this, using really interesting kinetic transformation. So that's what I'm gonna do today, to mimic this kind of structures using Houdini. And this is the sample that I made using Houdini, and I'll show you how it works. So it looks like this. So this is today's topic. So let's do this. Okay, so let me show you the overall process, how to create this kinetic ball, which is called switch pitch ball. So first you prepare the cube like this. Then set two kinds of grooves to each vertices in the cube. One with in this case, one with the blue one and one with the red one. And the difference between those two grooves is that it has different normal direction, which way those points should move. So the blue ones in this case is going outward from the center of this cube, and the red one is going from the corner points to the center. And as a result, when it transforms like this. So going back and forth from the cube shape to this kind of 3D star shape, you can actually mimic the structure, which is pretty similar to this kinetic ball. Also, you also need to have some spaces between the corner of the points, corner of this transformed cube. So in here, where the points are plotted, like the red one and the blue one, you create a triangular space like this, so that you can actually place some kind of circular panels or fins that you have seen in the video. And in order to attach the fins, you also need to have some branches on top of these structures like this. And as a result, first you place the circle panel on top of this triangular faces, then place these fins, attach these fins to the branch that you have just made on top of the structures. So as a result, you will be able to get a ball looking like this. And by changing the structures, transforming the structures like this from cube to a star shape, you can actually open and close a ball which looks like this one. So let's try to implement that using Houdini. Okay, first thing first, let's start by creating a basic cube. Okay, so let's create a geometry node and get inside. To start with the box with the size of 1 is fine. And then from this cube, I would like to have one of the corners being facing upward, so that as a result you'll have a more prettier orientations. So let's do that first. So in order to do that, what I can do is to get a corner information from these boxes, like maybe the minimum and maximum boundary information. Then use that. Maybe if this is the minimum points and if this is the maximum points, then you can get the directional vectors and use that vector to actually rotate this box. And let's do that now. And also I would like to also set a group to those vertices, each points on the cube, like I showed in the diagram for the red part and the blue part. So maybe these four corners, maybe this one and this one and this one on the bottom and this one on the bottom will be blue, and this one, this one, this one, and this one could be red. So such that, let's do that all together using point wrangle. Okay, so I'll name this rotate and grouping. First of all, let's do the cornering first. So set the group for each point based on its positions. So in order to do that, I will first retrieve the minimum position of the boundary and the maximum position of the boundary using a function called get boundary box. So I need to have minimum, maximum vectors and use get box function to feed those vectors to actually get the minimum and maximum position of this cube. Then let's find out the corners for these points on the bottom, the diagonal positions here, and if that's the position you pick for the bottom, then on the top it's the other directional points here and here. So let's give some conditions for that. If pt num is the modular by 2 is equal to 0, which means, as you can see, if you look at the point number here, let me make the text larger. So in this case, these are the point numbers, and this condition means that the point number is even numbers. So if the point is on the even number, and if the pt num is less than 4, which means it's on the bottom. So in this case, that will be 2 or 0. Or if a pt num, maybe I'm missing 1. If the pt num modular by 2 is equal to 1, let me open the editor. Okay. And if pt num is larger than 4, which means the points are on the upper side, then set one of the group. So I'll name this set point group corner 1 at this point number, and also set the normal based on its position of the point. So I'll just, since I want to make the normal direction coming from the center, so I'll just normalize the point position, which will give you exactly what I want. And else, I want to set another point group. Let's call it corner 2. And set the normal pretty much the same as this one, but in the reverse direction. Like this. Okay, let's check that first. Okay, I seem to have some problem here. I did a spell mistake here, so it should be pt num. Alright, now let's check the normal for the points. And as I can see, the odd number point, or in this case, on odd number points on the top part and the even number points on the bottom is facing outward. The normal direction is facing outward, and I cannot see the other points, so let's change the shading to the wireframe, and the other points are facing inward, so these seems to be correct. And the one that has the normal going outward is have the group corner 1, and the one that have the normal going inside is have the group corner 2. So that seems good. Now let's also rotate these box so that one of the corner is facing upward to make the final result prettier. Okay, let's open up the editor again. First of all, what I would like to do is to get the minimum, the direction between minimum and maximum points position. So that is pretty easy. Just make a direction and normalize the result, which is minus subtracted by minimum direction. And let's also make a matrix. And I will use a function called dihedral to change this minimum to maximum direction to facing upward, which means in this case y-axis. So as a result, you'll get a rotation matrix. So after that, you can rotate the point by multiplying this matrix like this. And as you can see, the normal direction is a bit off right now because since I have rotated only the point, so I also need to rotate the normal direction vectors as well using this matrix, rotation matrix. So this seems correct now. Yeah. Now also let's set the lengths from the center to the point, one of the point position, to set it as the radius of this box so that I can use it later for the radius for the sphere, which covers this whole cube. So I only need just one radius because every length from the point to each point on the cube should be the same, so I'll just set the radius attributes to the detail. So I'll set detail attrib 0 radius and just pick one of the points and calculate the lengths like this. Okay, let's check the geometry spreadsheet to if I have the radius correctly stored, and yes, I did. Okay, now let's look from the top side, and it is a bit off angle, so let's correct that so that this line is facing the z-axis. Alright, or is it the x-axis? Maybe x-axis. So in order to do that, you just use transform, and I only need to rotate on using the y-axis as a rotation axis. So I think it's here, and the angle that I have to rotate is around 15 degrees, maybe the other way. If I look from this side, that should be great. So this is the x-axis, this is the z-axis, and the line is aligned with the d-axis, so that looks good. So let's go with this. Now let's change the shading to the smooth wire shaded. And now right now I can see the face of the cubes, but I actually don't really need those faces, so I only need the edges of this cube. So I can use the convert line node to just pick the edge of this cube. So currently I have 12 lines out of this cube. And next, what I want to do is to apply some attributes to each lines so that it could be used as a guide to create a branch later on. So the branch will be attached on each lines, on the middle of each line, and facing outward 90 degrees perpendicular to this line. So going outward like this direction, for this line going this direction. So in order to do that, I would like to first set some initial attributes to each lines as a guide, because I'm gonna use it twice. So let's do that. Primitive wrangle. Okay, let me first explain what kind of attributes that I want to apply to each edges. So for each edges, for example, this one, what I would like to have is 3 kinds of directional vectors. One is that goes from this red point, which is on the group 2 in this case, and the blue one, in this case group 1. So from red to blue, I would like to have the direction vector like this first, something like this. And then I also want to have this group 2 vectors apply to the edge as well. And then using these 2 vectors, I could also calculate the perpendicular vectors by using the cross product. And then having these this directional vectors and the crossed out vectors, I could also do the I could also use the cross product again using these two vectors to create another perpendicular vectors based on those 2 vectors. So as a result, I will have 1, 2, 3 vectors from each line, from each line based on the position of the corner at group 1 and group 2 points. And that is the information that I want to apply to each edges. And those information will be used to actually orient or place the fin for this ball, kinetic ball, which looks like this one, and to each branch line, I would like to attach the fin. Like this, and so that I could be able to transform this fin together with the branch like this. In order to do that, you need to have the three information, which is a normal direction, up direction, and forward direction, to do this kind of really complex transformation. So that's what I'm gonna give to each edges now. Okay, so let's go back to the Houdini, and this is the primitive wrangle. I named this branch guide, and first thing, for each lines I would like to get the number of points, which should be total of 2 points using prim points at primitive number. And let's just get to position 1 and position 2. Also, let's get the normal direction of each point. Normal 1. At first point. And normal 2 at second point. Like this. Okay. Also create a empty normal vector, which I'm gonna use it later on to apply into each edges. And also let's create an empty directional vector, which is from the corner 2 points to corner 1 points. The direction from corner 2 points to corner 1 point. Alright. And in order to correctly get the direction vector from corner 2 to corner 1, I need to give some conditions here, because you don't really know whether position 1 is on the corner 1 or corner 2 at this point. So let's give a condition called if in point group, if the corner, the first point is on the corner 1, then set the normal from the normal 2. So this is the corner 1 point, and if this is the first point, then pick this normal directional point, which is on the other side of the line, and apply it to the normal. Okay, and for the B direction, and normalize from position 1 minus position 2, which is as a result going from the end point to the first point. So from point 6 to point 2. That's the direction that I get using this calculation. Now else, if the first point is on this corner 2, then the one that the normal information that I want to get for this for the edges is now a normal 1, because this is this one, because this is on the first point. This is the first point, and B direction is also the reverse side. So normalize position 2 minus position 1. So like writing like this, even if the line direction is on the other direction. I mean, if this is the first point and this is the end point, or if this is the first point and this is the end point, you still get the same result writing like this. Okay, now also let's get the midpoint position for the first one and second one position, so which is pretty easy. You can calculate it by adding 2-point position, multiply it by 0.5. Okay. Now, let's also create a direction going from the center to this middle point. By just normalizing the midpoint position, because the center of this cube is on the center origin 0, 0, 0. Okay, now also let's calculate the up vector by using the cross product between the normal vectors that I got here together with this direction vectors that I got from the midpoint. So, and let's also normalize it to give the length of the vector be 1. And also let's create a third vectors you named as forward, using the same cross product between a up vector, which I have just made, together with the directional vector going from the center to the middle point. So that's the vector that I want to make. 3 vectors that I want to make. One, let me show you on the sketches again. So let's say if this is the line here and this is the center. So the one going from the center to the middle point in that direction is their direction. And then you also have calculated the up vector, which is a cross product of this direction as well as this direction, which as a result should face somewhere like this, perpendicular to those 2 vectors. And finally, by creating a cross product between this upward up vectors and directional vectors, which is between this one and then this one, you create a cross product. The perpendicular vectors go named as forward. Now this one could be perpendicular, parallel to the first directional vectors, which is this blue one. But just to make sure that everything is on perpendicular, I'm writing like this. I'm calculating like this. So after that, I am going to apply this attribute, each 3 attributes onto this each edges. So set prim attriv and also, since I also made this B direction, which is going from the corner 2 to corner 1, I also want to apply that vectors as well for a guide, which I could use it later on. So first of all, I am going to create an attribute called prim direction, at prim num as b direction. Okay, and set prim attriv normal direction at prim num as direction. Set prim attriv this time upward vector at prim num as up. Set prim attriv, name this forward prim num forward. Okay, these are the four vectors that I want to apply to each edges based on the position of each corner points with the corner 1 and corner 2 group. Okay, let's check if I got the primitive attribute applied to each edges, and it seems I got it. So let's continue. Now the next thing I would like to do is to move each of the points, corner points of this box to initialize the position of the branch, the transformation. So let me show you the videos, captured videos here. So without these branches, you should consider that you only are seeing those circular panels, the pink one and the blue one, and assume that there's a connection between those pink circles and blue circles without these branches, without these those triangular branches. Then you can kind of see that there's much simpler structures in between those circles. And as you can see, this is the initial position of the structures, and if I move it so that the pink circle will come to the center, you still see the same kind of structures as before when the blue circle's on the center. So just transforming in the same manner, like this. So what I want to make here is to create an initial status like looking like this without those triangular branches. So that is pretty easy. You can create a point wrangle. I'll name this init branch. And what I want to do is to move the corner 1 points. So the points which is on the corner 1, which is this 0.2, 0.7, 0.5, and 0.0 going inward, so that it will come to the center point. So the origin position, which is on the 0, 0, 0 position here. And other one going upward or outward. So for the 6, the corner 1, corner 2.6, 3, 4, and 4 and 1 going in outward. So creating like things like a tetrapod like shape. And in order to do that, I could write, first of all, I need to determine how much each point should move, and that is pretty easy because each point position, each distance from this origin position to the each point is the same, so you just calculate the lengths between lengths of the vector point. Then let's apply this max length value as a float attribute to each point, and then use this max length attribute together with the negative normal direction to actually move those points outward and inward like this. So for corner two groups which have a normal going inside, we'll use a negative normal value, so going with that goes outside like this, and the point corner, the point that is on the what is inside the corner one group will go inside because it's the negative normal direction, with the amount of lengths for the point, so the point will go attach to the origin position 0, 0, 0 like this, and as a result you'll have a full line like this is the initial branch. Now it's a bit different than the physical structures, because in a physical structures you wouldn't get this kind of simple line structures, but it's a bit more complex because there's a gap in between those three lines. Currently you have three lines for each cover overlaid lines here, but right now it's totally overlaid in this virtual display in this Houdini preview, but I will gonna fix that later on using some simple transformation. But currently this is okay. So this is the initial setup to set the shape. Now the problem is that by just moving those points using the normal direction together with the point lengths, point position lengths, each length of the edges has been changed from this initial box. So as you can see in the video here, the captured video here, since this is a physical toy and the connection between each circles, like blue one and then pink one, is rigid, and it does rotate with on the rotation axis here, but actual length of the connection between those circles never changes. The length never changes because it's rigid. But in this case, by moving the points inward for the corner 2 and outward for the corner 1, then, or maybe the other way, it changes the length of the edges. So that is a bit of a problem, so I have to fix it. So in order to fix that, what I am gonna do here is to first calculate the updated lengths of these edges using measure by checking the parameter. So you have a parameter value here. Now after you have got the parameter, you also have a value called rest length, which is the original length of the box edges. You've got it by using this convert line. So after you apply the convert line, you had this rest length attributes for each edges, which shows the actual length of these box edges. But then by using this point wrangle, moving each points based on the corner position, the lengths have been changed to something like 1.73. So I need to fix those parameter to become same as the rest lengths again. So I can do that by just using simple transformation. I could either use transform node or wrangle node. In this case, I'm just going to use a wrangle node because it's more easy to access the attributes. So I'll name this init rescale. Okay, and first thing, I'm gonna get the list lengths from the primitive value. Each primitive value has the same rest length, so I'm just gonna get it from the first primitive. So for the rest length is equal from primitive 1 and primitive 0. Then also let's also get the current primitive length from the parameter attribute. Like this. And so what I want to do is to scale it so that the actual length of the final initialized structures have the size of rest lengths for each edges. So I need to, let's calculate the scale ratio by dividing the rest lengths by current lengths. Okay, there's nothing here. Right, and I can just multiply this ratio to this point position, which will, as a result, will just scale each point position based on the scaling ratio, like this. So now it becomes, now each edge's lengths become same as this rest length. Now also let's multiply this max length attribute by this ratio. Maybe I could use it afterward. And also for each points, I am gonna attach a attribute called ID based on the point position, pt point number. Okay, let's check the point attribute. I have IDs, I have max lengths, and I have, let's also calculate the actual edge lengths using measures again to check if the parameter has changed. And check the primitive. And the parameter has become 1, same as the rest length, so that seems okay. Okay, that seems okay. Now let's just connect this with the null node named as init branch. Maybe I will access it later. Okay, let's resize this window a bit. And let's color this yellow so that I can use object merge later on. Okay, let's group this. So this is the initial structures that I got. Now the problem I got here is that, as I told you, there are actually 3 lines overlaying each other to each of the line that I can see on this Houdini preview. And actually those lines cannot be overlaid physically. If you look at this video, if you look at these captures, try to ignore the triangular branch here, but as you can see, for each connections between the pink one and blue one, 3 blue ones, you should see a line here, line connection here, and those lines should never be overlaid physically. It should never touches, because then you cannot really rotate it like this. So I want to do the same thing as in the Houdini. Right now it's touching together, but I do want to separate those 3 lines a bit off outward. So let's do that. First thing I would like to do is that each point are connected to each other. So I want to make each point unique so that I can separate those lines and point. Each line should have a unique points. So I could use the facet node to unweld the points by checking the unique points checkbox. And next I could use a point wrangle and do the separation for the lines. The rule here is that when I do the separation for each lines going outward, the length of the line should never be changed, because physically it's not possible, because it's not a gummy material, but it's a rigid material, plastic material. So even if you want to offset those lines outward, you should never change the lengths. You should keep the lengths of the lines to the same. In this case, 1. So keep that in mind. I'm gonna do in 2 steps. First, using a normal vectors of the corner 1, and then for step 2, use the vector normal vector information for corner 2. So use those 2 corner information. I can move on one side first, one corner direction first, and other corner direction later on step 2. So for step 1, I will check the corner 1. So let's, on the group filter, I am gonna name it corner 1. And in this case, I'm not sure which one is the corner 1, so let's check by using the delete and set it to point, and corner 1, select non-deleted. Okay. So so the center points seems like is the corner 1 point, and if I change it to corner 2, am I only seeing? Okay, so the corner 2 is the outward points, the points which is on the corner, outward corner. So keep that in mind. First, I am going to look at the corner 1, which is on here, and if I visualize the normal, there is like 4 direction for the points on the center, because actually there are a lot of points gathered in this point position, center position, maybe 12 points. So keep that in mind. First thing, not 12 points, maybe 4 points. Okay. First thing I would like to do is get the neighbor of each point on the corner 1. Since I used the facet the neighbor should be only one, the point should only have one neighbor because it's just the one line. And I'm gonna go through all the neighbors, even if I know that there's only one neighbors. Just to make sure, so that it still works. Get the neighbor point from the neighbors and get the position of the neighbor point. So if I'm looking at here, then the neighbor points should be either this one, or this one. So I would like to get the point position for these points, which is on the outside. Vector position equal point P at the neighbor point number, and I'll change the point position for each of those neighbors with the normalized vector of this point's normal direction. I mean, I might not need to do this because this normal direction should already have a length of 1, but just in case, and multiply it with a amount of move you specify, so how much you want to offset outward. Then finally update the point position on the neighbors, this one, this one, this one, this one, using set point attriv with the updated point position. Okay, save this. Okay, I was missing the point number here. Right, now I don't have this CHF move, the move channel to this vex wrangle yet, so let's promote this, click in here and changes this value. Now you can see that the neighbor points are offsetting using the normal direction, which I have referenced from the center, like this. Now this is a bit still problematic because the center point is not changing position, so I also want to change those position. But I can do that by just calling current point position plus current normal, same as this one. Maybe I should normalize this as well, just in case. And okay, it looks good. So all the points has been offsetted outward based on the corner 1 normal direction. And because for each lines I'm just using the same direction with the same size, the actual size of each edges should not have changed from the original structures like this, looking like this. Now, as you can see, the problem here is that this points here, it's still touching on the center, on the corner 1. So I'm gonna do the step 2 to separate those 3 lines outward the same distance as this move value, so that I could have a triangular space similar to this corner 2 positions. Now before doing that, let's make a null controller to actually have those move parameter, which I can then use it later control the whole setup. So I'll name this, how should I name this? Maybe a sep distance. The number could be any number for this separation numbers, but it does actually changes the way the ball looks like, because it's you control the space of the structures. By doing it, you kind of change the composition of the fins and the circle panels. So, which is also really fun to look at. Okay, so I have just copied the parameter. Let's paste it to this move parameter. Right. Now let's do the second separations using another point wrangle. And name this sep2. And for this one, I am going to look at the group corner 2. And what I'm gonna do is pretty much the same here. So I am going to copy those code from the sep1, paste it to sep2, and promote the move, copy this parameter here to this one. And the only change I have to give is that since it's going inward right now using the normal vectors, so I have to change the direction of the normal direction to the other side, the reverse side, by changing this plus equal to minus equal. And now you have got the result that we want. You have this triangular space between the corner 2 points, corner 1 point, and corner 1 points, like this, and you still have the same length as before when it was like this. So that's good. So this is the initial condition of the structures of this switch pitch ball. Now let's also name this initial separation. Let's color this. Okay, so after this, actually the next thing I would like to do is to create a sphere based on the size of this structures. So by changing the value here, the separation distance here, the size of the sphere should change based on the end point position on this each edges. So let's calculate the radius of the sphere by checking one of the edges and set the length from the center position, origin position 0, 0, 0 to the end of the edge point position be as a radius of the sphere. And that is pretty easy to do. I can use the point wrangle, and since these outward points are the group in the corner 2, so I'll filter the point with the corner 2 and just set the set detail attrib radius with the length of P point position. So I'm updating the radius of the detail attributes here. So I guess I didn't need it to set the radius beforehand. Now name this radius and check if I got the value correctly. Going to the geometry spreadsheet detail, and yes, I have 1.29522 as a radius of the sphere, and this value should change based by changing this separation distance. If I look at it, it's right now 1.5. So let's connect the null node here. Name this red. Also make it yellow. And let's create a sphere. And I will make it as a polygon here. And let's show this. Now I also would like to change, maybe not the polygon, but maybe to polygon mesh, so that the mesh looks like this. It's more cleaner when you do the Boolean operations. So also let's increase the value of rows and columns to make it a bit more high res. It's pretty up to you, but I would prefer having it larger value. Okay, now let's scale this sphere based on the radius which is inside this detail attribute. I could either use transform or wrangle. Maybe I will try to use this transform in this case. I mean, it's just either way is fine, I guess. In this case, I am accessing the detail from the rad null node, their attribute called radius for the first value. And I have successfully imported the attribute value, detail attribute value called rad. And if I overlay with the structures, I can see that the sphere is correctly covering the lines. So that is good. Okay, now let's give another null node to this transformed sphere named as base sphere. And I think I'm gonna use it later on a lot of times. Okay, now next thing I would like to do is to create a initial position of the branch together with a information of a vectors such as normal vectors, up vectors and forward vectors in order to lay out or orient or place the fin for the switch pitch ball, the kinetic ball. So if you look at the capture video, right now I have created a structural line between these circles, such as this blue one and the pink one. And I've just created a straight line between those two circles. But what I want to create now is this triangular looking branch, which is the actual position where you want to place, where you can place this fin for the pitch ball, like this. So as an initial position of the fin, I just want to create the tip point of each branches for each structural line which connects two different circle plate. So let's do that. So if I show you the sketch, what I want to do is for each primitive, like this one or this one, each lines. I want to create a perpendicular line like this, and say this is the circle, this is the sphere that covers the whole structures. The length of this perpendicular line should be collide with this sphere. So this is the length that we want. And then at the tip of this point, the branch, I want to set the 3 vectors which gonna be used to place the fin. So that will be normal vectors, up vectors, and forward vectors. And by having that, you can later on place a fin like this using those orientation informations in the correct position and the correct rotation. Since this every branch has different angles, the orientation is going to be really complex, so you need 3 vectors in order to orient this same fin to each places correctly, like the switch pitch ball. Okay, so let's do that. Currently the structure doesn't move, so what I'm just gonna make is the initial position of the branch as a guide, and I can do that by using a primitive wrangle and write some code which is a bit similar to what I did before, but I'll do it again. Okay. Now, how should I name this? Let's name this init branch 2 or something. Okay. Now let's write it. First thing, for each primitive, for each lines, I would like to get a list of point numbers using prim points. And I also want to get the normal vectors of each primitive, which I have applied before. So if I look at each primitive, I should have these normal vectors. I don't think I can display it with the lines, but it was a normal vector which goes from the center to the middle point of the line, each lines from the squares, I think. So that was done here, I think, yeah, using this script. Yeah, so this is this is the one. So that was from the center point to the middle point of each primitive, and that's the value that I'm getting here as an end dr and direction. Then I'm gonna get a position 1 and position 2 from the line. Position 2 point. Also, let's get the normal vectors from this point number. Alright, and as we did before, let's get the empty normal vectors and the v direction vector, which I am going to feed it based on the point group. So either if the points is inside the corner 1 group or corner 2 group, I will change the value here. So if the first point is inside the group called corner 1, then feed the normal with a normal 1 in this case. A bit different than before. B direction is normalize, and position 1 minus position 2. So I think these points on the center, these triangular points on the center position, rather center position, will be corner 2, I think. And these are, let me check. Let's check by delete unselected points and corner 1. Okay, I was wrong. The points on the center was corner 1, and points outside the center, which means touching the sphere, is corner 2. So if the first point of the line is on the corner 1, then feed a normal from normal 1, which is the normal from this point. This one, which goes outward. And the B direction is position 1 minus position 2. So if this is the corner 1, then the position 1 minus position 2 will be the line goes from up to down for this line. So that's the B direction. And else, if the first point is inside the corner 2, then just do the other, just use the other normal. So if this is the first point, then the normal will be the other normal, so this one, so still the same one. And B direction will be position 2 minus position 1. So either way, the result will be the same direction based on by checking whether the first point is on the first corner, corner 1 or corner 2. Right, and also let's create a new up vectors by calculating the cross product between the norm that I have just got. So for these outgoing vectors is gonna be this norm, and direction which I have got from the primitive which I applied before. So as a result, you'll get a new up vectors. So the normal, this n direction should go from center to somewhere on the lines here. So the cross product result between this direction and the direction from the center gives you a perpendicular vector which goes either this way or this way. If you look from the top, either go this way or this way downward. So that's going to be our new up vector. And then I would like to rotate this up vectors 90 degrees using a B direction as an axis. So this line, this vector will gonna be a axis for the rotation, and I would like to rotate the up vector that I have just created using cross product, using this V direction as a axis 90 degrees, so that will be a new normal vector for the branch point. So first let's create a matrix, and using rotate function to rotate this matrix by 90 degrees, maybe to the negative 90 degrees, using the B direction as a rotation axis. And then create a new normal by rotating the app vectors that I have created. Right, so now I have two vectors. One is, oops, am I missing something here? Vector, okay, gotta be matrix. Okay, so I have two vectors now. Right, new app and new n. And let's also normalize the cross vectors just in case to make the size 1. Right, now I want to make another vector called new f, stands for new forward, by making a cross product, using a cross product to calculate a new n and new up. So normalize cross new up and new n. So as a result, you'll have three vectors to show a plane information. So x, y, z axis. These gonna be an x, y, z axis. New up, new n, and new f. Now, after I have created this information, I wanna create a position for a tip point for the branch. So let's do that by using an intersection. So let's first create an empty branch position vector, then also create an empty UV information, and let's use the intersect function in order to collide with the base sphere, this one, from the midpoint of the lines between start point and end point. So let's also make the midpoint vector mid equals to position 1 plus position 2 times 0.5. And then from the mid position, and the direction should be going from this point to the perpendicular of this line. So it's gotta be new n, which I've created here, this one. And since I'm gonna use the intersection, let's make this length a bit really large so that it will collide. It will intersect with the sphere, then feed the intersected position to the branch path and UV, which I don't really need. Okay, now after I got the branch position, let's create that. Let's use that position to create a new point using add point at branch position. Now let's check. Okay, now I do see these points here. Can you see it? Right here. Okay, now after I created the point, let's also check if the point is on the sphere, and yes it is, and I think it is perpendicular to this line as well. And for each primitive, for each line, the new point has been created as a branch tip point. Okay, Now, after I created the point, I also want to set some attribute to each of the point, which is the 3 vector information to know which way it's directing, which way it's facing, so that I can use those information to orient the fin, place the fin later on. Okay, so let's do that. First of all, I am going to set the group as well to this point, newly created point. So set point group, named as branch, and to the newly created branch point. And let's set some attributes to this point. So set point attrib up branch pt as a new up. Okay, also set point attrib capital N stands for normal as new normal. Okay, set point attrib this way forward branch pt and set it as new f. Right. And finally, I also would like to set a primitive attribute to this line, which is a length between the midpoint and the tip point of the branch. So I want to calculate this length of the branch, since that branch length should not change as well, same as these lines, which is going to be a structure. So set prim attrib branch length prim distance between midpoint and the branch position. Okay, I have a spell mistake here. Branch pt. Okay, and I can currently see the normal vectors being applied to the branch tip point. I also want to show the up and forward to check if I have got it correctly. So let's go back. Let's go to the marker option and create some new markers here to actually show the up and forward. So for the app, let's visualize it with the, I don't know, red, and make it vector. It became yellow though. Wow, that's okay. Close, and let's add another marker for the forward. So forward, and use it as a vector. Set the color to red and attribute as forward. Okay. Now I also want to make sure that these forward vectors and up vectors are normalized, and I think that's correct. It's a bit long to visualize, so let's make it a bit smaller visualize wise. So these ones, I guess let's set the same size as normal vectors. So so these are the tip points together with the rotational information for the fin, and we are going to use this later on. It's pretty important, and that's the key point of this definition. Right, now let's group these together again, and let's continue. Okay, so what I have just created is the initial position initial setup for the structure of the kinetic ball, switch pitch ball. And from now, I would like to actually give some interaction to this structure so that I can move like the toy here. So from this base position to another setup so that the pink circle will touch together, and by changing the rotation of this structural lines, changing to another form so that the blue circles will touch together. So going back and forth. Like this. Okay. Now, in order to do that, I am going to refer to a one that I have created before, which is this one, init branch, which was still touching, and those lines were touching together, but I am going to use this one in order to create an interactive rotation, interactive kinetic movements. Because that will be more convenient in my way. So first of all, let's go back to where we have ended, and let's connect a null node to this initial branch 2 and name this init branch 2. And color this with yellow again, and let's bring up this initial branch 1 using object merge. So I'll name this init branch, and let's color this green, and let's refer to okay. If I click this, let's select init branch null node, and it will bring up this lines which was still touching together. And what I want to do is to first transfer the attributes from the init branch, initial branch, which I have separated the line away with some parameters, and I am going to bring some parameters such as branch length for each primitive, so the length from the midpoint to the branch tip point, as well as the radius of this whole structure. So let's transfer that using maybe primitive attribute, since I wanna transfer it for each primitive. So primitive wrangle, and connect it to this one for the first input, and connect init branch 2 to the second input as a reference. And then let's write a code here. So first of all, branch length equals to primitive second input named branch length at the same primitive number. Okay, and also let's also bring up the radius value from the detail attribute from the second input. So route radius is equal to bring up from the detail second input radius, and then use that value to set a new detail attribute to the current geometry. as a radius, same name radius. So I'm just passing the primitive and detail attribute like this. Apply. Let's check. Let's go to the geometry spreadsheet first. Primitive wrangle. Do I have a branch length? And yes, I do. And also the detail. And I do have 2 attributes. So that's good. I'll name this transfer attrib. Okay. And next, so here comes the part where I want to interactively move this structure back and forth like the kinetic toy. So what I'm going to do is for the center points, which is placed on this center position, I'm going to move this point outward using this normal vectors. And for the points which is on the outside, which is touching the sphere, I want to move these structures inward toward the center. So that's what I want to do. So using maybe some sliders, I want to be able to move those points back and forth by changing the value of the sliders. So let's do that. Let's do that by using a point wrangle. And let's name this move for simplicity. And for the points that I want to move is corner points, so corner 1 and corner 2. And let's do this. So what I'm gonna do is pretty simple, just updating the position using the normal direction times the maximum length applied to each point. So that's the maximum length that point can move, so that if the point go from the outward to the center, it wouldn't go over the center point, so it would stop on the center point. Then multiply it with some movement input value, which is from 0 to 1 as a float number. Okay, and I guess I also have to multiply it with 2 because the max length was the length between the midpoint and the end point. So if it's multiplied by 2, then it should be the whole length. I think that was it. Let's check. Point max length was 0.5, so I think that's correct. Yeah. So I'll have multiply by 2, and also let's promote the move sliders by clicking this button. And as a side attribute, I am going to add an ID to each primitive, each point, derived from the point number. So for ID, starts from 0 to 8. Okay. Now let's check the movement by changing the value here. And I can clearly see that the point position of the square has been transformed as I want it, and this movement is same as the kinetic switch pitch ball. Now there is one problem here. That is, if I change the value like from 0 to 1, actually the lengths of each edges are changing. So in this case, let's check that by connecting the measure node, measuring a parameter. So when the move value is 0, then the parameter for the primitive is 1.73, 3205, but if I change this value, move value to 0.5 or something around that, then the parameter changes to 0.577, so it got smaller. So that is a bit of problem because, as I told you, the structural line should not change its length. So in order to avoid that, I have to rescale it as I did for the initial branch lines, initial structural lines. So I have connected the parameter to check the current lengths for the lines and do some rescaling based on that parameter together with the rest lengths, where this should be the final result for the final length for the structural line. So, which is pretty much the same as I did before for the rescaling, which was done somewhere around, where was it? This one? Yeah, this one. So let's copy this and connect it here. Name this rescale. And just remove some of the code which was only for the initial branches, initial structures. So left with only the multiplication in order to fix the length of the edges like this. So by doing this, if you change the movement of this cube point position, you are keeping the line length always the same, even if you do this kind of transformation. And this movement is exactly the same as the kinetic movement of this switch pitch ball. Surprisingly easy. Yeah. Now that I have rescaled the point position or the edges, what I have to do next is that, as I did for the initial branches, I also need to offset these lines, which is currently touching on the tip point of each structural edges. So as a result, I want to do an offset just like I did for the initial branch, which looks like this line, so that I could have a triangular gap in between the lines, 3 lines, both for the corner 1 and corner 2. Right, so let's do that. And what I am going to do is pretty much the same as I did for the initial branch. So I am guessing that I could just copy the one I used before, which is separation 1 and separation 2. So this one, together with the facet. So copy this, connect this, and looking like this. So it's keeping, as we did before, it's keeping the edge lengths the same, even if you have offset it. And if I move the structures, so that 0 position, if the move value is 0, it's same as the initial position of the branch, initial position of the scale, so same as this initial branch 2. But then if I move this value to bigger than 0, then it will change its structures back and forth like this. Cool. So, and you can also tell that the size of this triangular connection, which which you can see here or here, is preserving its area. I think you can see it. So that's pretty much the point here in order to create a structural kinetic composition. Now, after doing this, let's give some null node so that I can access those information later on. Now, after the rescale, I'm gonna give a new null node here, and let's name this transform bones, and call it with the yellow. And also after the separation, I am going to give another null, and let's name this separation bones. Set it as yellow. Also, for the movement parameter here, I wanna give a controller null node some parameters so that I can control it later on. So let's go back to this controller, edit parameter interface, and maybe I can forbid linking parameters here, uncheck it, and then go back to the move parameter here and drag and drop this movement here. Okay, I'm gonna make it lowercase, and from 0 to 1, that's okay. Now let's check if it works okay. If I change the movement, yeah, it does change. And if I change the offset, it is also changing the offset value. Now that looks good. Okay. Now let's give some grouping for each network. Now what I'm gonna do now next is to create a branch line for this transforming structures. And I have already did create an initial branch using some coding here. For this one, it was just a point, but then the one I'm gonna do next is to create an actual line between those branch tip point and the midpoint of this structural line. Now, so basically the whole coding stuff is pretty much the same as this initial branch that I'm gonna do next. So I am going to just copy this thing, init branch to code, and then bring it down here. And I will name this branching. And I am gonna modify it a little bit for this coding. And let's check where I should change. Now, initially, those values should be okay. And everything up to these lines should still be okay. And I have this branch position. Now, I cannot use the intersection in order to define the branch position now, because since this structure now is gonna move based on the move parameter, I set it on a new controller. And if the angle of the structure changes, if the position of the midpoint changes, then if you use the same intersection function as I did for the initial branch, then the branch length of this intersected position, the distance between the midpoint and the intersected position will change. And that is not what I want, because as I said, the branch is also a structure of this kinetic ball, so the length should not change. And I have already set the branch length, which I have retrieved from the initial branch using intersection, and I have applied it as a branch length into a point wrangle, I think, or primitive wrangle, maybe primitive. Okay, as a branch length, and saying as 0.82 or something. So this is the actual branch length which I have retrieved when I created the initial line structures. So I am going to use this value in order to create a branch on moving structures without using intersect function. So remove these, and the branch position is equal to mid position plus new n, which is calculated here, which is the normal direction, which is a perpendicular direction from this line, and then times f at branch length. Right. Now, after I have created the point, this time I have set the branch point group, branch point new up, new n, new f, that's okay. And forward as well. I don't need to set the primitive attribute for the branch length because I already have it, and it's not gonna change. The new thing that I'm gonna do here is to add a line between the tip point of the branch and the midpoint. So int prim add, I'll just name branch line, add prim polyline mid pt to branch pt. Now I think I need to also create a midpoint position, so let's also do that maybe around here. So int add int mid pt equals to add point mid position, or mid, just mid. Okay, now that looks like the one I wanted. And finally, let's set a group to this branch line, set prim group as a branch. And also, I want to give those lines the baselines of the structures as a as a new group called structure. So set prim group structure prim num 1. Okay, now let's check by changing the move parameter here, so that if the branch line is not changing its length and being perpendicular to the structural line. So, okay, what's wrong with this? Why am I seeing two lines here? Sometimes it happens showing some ghost geometry, and I am not really sure why. Okay, let's cut, undo. Oops. Okay, I gotta reopen this file. Okay, enough with the less visual points and lines. Let's start creating a bit more interesting stuff. Let's give these points a polygon. Now, the one that I want to make now is those circle plate for each point, both blue and magenta colors. So let's do that. And I am going to create that polygon or geometry from a sphere. So first let's give one sphere and set the size, set it to maybe polygon frequency to around 6, something like this. And let's control the size of the sphere using some parameters that I am going to create inside a controller. So let's do that. I am going to name the parameter called hole size, which is going to be the size of the circle panel. And that could be from 0 to 1. And let's set it to around 0.3 for now. Copy this parameter, go to the sphere, and then paste it to the, let's give another node transform, and paste the value, parameter value to the scale x, y, and z, x, y, and or maybe let me just delete those. Give everything 1 and let's paste the value to here. Sorry. Then for just the z direction, I am going to scale it 0.5 so that it will become like a marble chocolate. Right, now after this, I am going to cut this geometry using the basic sphere geometry, which I have created before, just same as this one. So I'll copy this one, base sphere, and what I want to do is to place the this marble shape should be cut with the base sphere so that when it aligned outside the sphere, then it will have the same curvature as this base sphere. So in order to do that, what I'm gonna do now is to first transform this base sphere to the z direction so that it could cover with this small hole size sphere. So the value that I'm gonna move is minus at $max z max. Then it will cover up the marble chocolate like shape like this. The next thing I would like to do is to get the intersected geometry between those two spheres. So I can use a boolean, connect those two geometries and make the operation intersect to get a geometry looking like this, right? And finally, I can just place this geometry to the point information that I made here, circle PTS, using copy SOP. So let's do that by using copy 2 points. Copy this to this points, and as a result, I will have those geometry placed on the point with the color transferred, and connect the normal together with the null node named as circles. Let's color this yellow, and let's check out the movement of this circle plates, whether it's moving correctly. So if I change those value, yeah, it seems to move correctly, going inward to outward. And let's connect this sphere together with the structure that I made before, this one. So it's given a object merge. So for this one, I'll call it structure. Another one, object merge. Oh, not this one. A circles. And refer to the structures and circles from the null node. And merge it together to see two geometries moving together. Okay, so now if I change the move parameter here, both structures and the center circle is moving together, and that is the basic structure of the kinetic ball, the switch pitch ball. And I think the movement is pretty much correct. Now I might want to change some values for the curve here. Maybe for the structure, maybe 0.05 to 9.95 to make the length of the structure a bit more longer. Cool. So almost there. The final step is to create this fin geometry next. So let's do that. Alright, let's group this out together, and let's group these together so that I can see that this is this place I'm making this center circles. Okay, now let's get into creating a fin, rotating fin, which connects to the tip point of these branches, end of these branch lines. And that is the most fun part of this definition. Now first of all, let's give an object merge node. Name this init branch. And then color this green. Refer to init branch, which gives you I guess not this one. What I wanted is for init branch 2, I think. Let's check. Yeah, this one. Let's also show up the up and forward and normal. So this is the geometry init branch information that I want in order to create the base fin shape. And from here, I just need one reference, one of the branch tip points out of these maybe 12 points, 12 branch tip points, in order to give a rotational basis. So let's do that first by just bring up the branch point out of these points. So delete non-selected, set branch and entity to points, so that I have only branch points right now. And then just pick one of the points from these 12 points, and let me show some numbers, and let me just pick one of the points out of these. And I am guessing picking up something like number 5 is good. I mean, it could be any points, but I'll just pick this number of points because the upward vector is facing and y direction is, I think it's pretty easy to use compared to the other one. I mean, still, it's anything is good, but I'll just pick the 5 one. So give another delete. Oh, not this one. Wait. Delete. And non-selected point and 5. So that I have picked one of the branch tip points, and I will name this as a null node branch guide. Let's color this yellow. Okay. Now, after this, let me bring up the base sphere geometry using another object merge. Let's call this base sphere. Color this green. Bring up base sphere. Okay, let's hide those. And also create a box in order to cut this base sphere. So set the size to 10 so that it will cover up a whole sphere, and also translate to -5 on the y-axis so that it covers half size of the sphere currently. Now, after doing that, let's move this cube to this branch guide position. So copy 2 points, and maybe currently I don't need the normal direction or up and forward for this branch guide, so I am going to add, because having those information will let box rotate, so that's not what I want. So currently, no, not this attribute blur. I am going to delete all the point attributes from this branch guide. I just need a position. I'll use the this one, and to this point I want to move the box to here. Okay, now by moving those blocks I want to cut the sphere, the base sphere, to create a base shape of the fin. Right, now what I want to do here, connect, use the boolean and connect sphere first and box second, and I would like to keep set the sphere as a surface so that I don't have to have the back face like this. So let's keep the first set A as surface so that I can have open disk like this. And check the position of the branch guide if it has been trimmed on the right position. Yeah, so this is the tip point of the branch. Initial branch came from here, and which covers up the one of the structural line like this. So you can assume that this disk is covering each structural line just like this umbrella to create kind of a sphere-like shape as a result, if it covers everything up. Right, now after doing it, currently it's just a disk and doesn't really like the fin that I showed you on the capture video, so to transform it to something similar to a fin shape, I'll do some modification, kind of a precision modeling stuff using Houdini, which is a bit one of the hard thing to do in Houdini, doing modeling stuff, kind of a manual looking modeling, but I'll try to do as much as possible to make it procedural. So first thing I need to do is to remove all the shared edges here, shown here, so from the disk. So I am going to use the divide. Check, remove shared edges, and then sorry. I am going to project this shape to a XY plane or XZ plane by just using the simple vex script. I'm gonna name this project. By just modifying the Y position to 0, it will just project to the XZ position, XZ plane. Then after that, I'm gonna make a hole for the circle plate on the center so that the one that we made before could be visible. So let's create a hole for the circle for in order to open up the hole into this disk, so it will look like a donut. Right, so let's give a circle, and before making a hole, I think I also wanna make this whole disk 1/3 shape, so trimmed as a 120-degree pizza. So let me just do that first. So in order to cut it at 120 degrees, my method here is going to use a polygon which have six sides. So make it XZ plane, make it polygon, have 6 divisions, means 6 edges, and scale it to something a bit big. And for the center position, I think I need to change the Z size here. Currently I have something like this. Now let me change this center to 2 and also rotate it 30 degrees. Right. Now I also would like to offset this position of this 120 degrees cutting guide to Z direction, maybe to the right side, so that I could have a little bit of gap between the other 100-degree surface, other fins, I mean. So let's make another parameter here, calling whole offset, and that could be from 0 to 0.1, I think. And set some value here, go back, and add this parameter here, so that I have a little bit of offset outside to the right side. Okay, now if I look at it, it's facing downwards, so make it use reverse to make it facing upward, and finally do a boolean to create intersection between the base circle disk together with the guide which cut off the disk into 120 degrees. So let's do a boolean, and both are surface. So let's set as surface for both and do intersect. Now I have this kind of 120 degree pizza-like shape. Now next thing I would like to do is to create a hole, create a center hole around here, so that the circle plate that I made before could be visible out of this hole. So let's create another circle, make it XZ plane, and the radius is derived from the hole size, and maybe together with the hole offset size. So let's go back to the controller, just copy this hole size first, which is gonna be the radius of the base circle plate. So paste it to this uniform scales, and also you also want to have some gap between the hole, I mean the center circle, to get to these disc outside, the fin outside. So you want to add additional offset value next. Let's just change this to offset, right? And let's set it to polygon. Set some divisions to some high numbers, something like 36, right? And let's do a boolean again. Boolean. Subtract from this shape with this one using surface, surface, subtract, and that's good. Alright, now let's call this base wing or base fin. Now this is not yet good enough because, as you can see from the video captures, the shape itself right now is a bit too rigid, too hard, too pointy compared to the one I'm showing on the capture video. So it doesn't really have to be like exactly the same shape, but I want to make it close to the original shape procedurally. So let's try to do that. Okay. So at this moment I will going to group this together. Okay, so let's try to modify this shape a bit more interesting than this donut-like, cutted donut-like shape. Right, so starting by converting those surface into a collection of lines. I am going to convert this into a line here using convert line like this. And if I look at the point, there are many points on the arcs, but they're only like the straight line here and here on the edge only have 2 points to create one line, straight line. So what I want to do here is to pick those 2 edge lines, this one and this one. So in order to do that, I am going to first sort the edges by the attribute called rest lengths, because if I use convert line, each line should have a attribute called rest lengths, which is a length of the line, and I'm going to use the sort to sort out the primitive by its rest lengths, and I am going to check this reverse primitive sort so that it will be sorted from the biggest length to the lowest. And so that means if I just pick the first and the second one, it will be this longest line edge. So delete node selected, 0 to 1 primitive, and I have got these 2 lines here. Now let's also sort this line by a x coordinates. So the horizontal line here is the x. So let's sort this out by an x, just to make sure that you have lines, you know which line you want to control. Now what I want to do is to make those lines a bit more smoother. So I am going to make it like an arc-like shape later on using some wrangles. So but in order to do that, I need to have some more points on top of this in order to construct this line. So I am going to give a resample and divide the curve with the length maybe 0.0 something like 5. Right, and also I would like to have a tangent vector for each point, which in this case going from left to right, so this direction, and this one should go this direction. So I could just check this tangent u vector, tangent attribute here on resample. Right, now let's go to the primitive wrangle in order to change the shape for each arcs. I mean each lines to make it like an arc. So primitive wrangle. Let's name it, make it arch. And let's write some code here. So we have two primitive, and left and right I would like to change some a bit of difference. I want to make a bit of difference between the left one lines and the right lines. So let's do that. Let's open up the editor. And first thing first, I am going to bring up all the points from the primitive using prim points. Right, and also get the length of the primitive from rest lengths. Okay, now do the loop through all the points belongs to the primitive. Right, and let's get the point position. Using the point attribute, point function at the PT. Also, I would like to get the starting point position for each primitive. So that will be, I'll name it as pos as a starting point, and I just need to get the first point number from the PTS. Right. Now also let's get the tangent vector from each point, which I have retrieved from the resample. So point 0 p, no, not p, tangent u at p number pt. Right. Now what I want to do next is, let's say I do want to I want to make some kind of arc-like shape like this. So what I can use is some simple, maybe not that simple, but trigonometry, and in order to create an angle, I mean the arc-like shape. But first of all, I would, in order to do that, what I need to do is to move those points perpendicular to this line direction, which is tangent vector. So let's start by creating a perpendicular vector first from this tangent vector. So I am going to rotate this tangent vector by 90 degrees. So I am first gonna make a matrix, rotation matrix, starting from ident. Rotate this matrix by a radians of 90 degrees. With the y-axis, and the result perpendicular direction will be, let's normalize it first, and will be a tangent vector multiplied by a matrix, rotation matrix. So rotate the tangent vector 90 degrees and make it normalize to set the length to 1. And this direction will be the perpendicular direction, which is facing like this. Okay, now For each point I need to calculate an angle in order to move how much it should move to the perpendicular direction. And the reason why I'm using angle is that I am going to use a trigonometry, either sine or cosine, to create a arc-like shape, sphere-like shape, circle-like shape. So let's calculate angle first from the number I divided by float length PTS minus 1. So as a result, this value will be from 0 to 1 depending on the position of the point, and multiply it by pi. So and the starting point will have angle 0, the end point will have an angle pi, which is equal to 180 degrees. Right, now let's also have an empty variable called x and y for the float as a float, and then if prim num is equal to 0, then which means this is on the left side of the the line is on the left side, and if it's not 0, then it's on the right side. So if it's on the left side, what I want to do is to use some functions like this. For x, do a calculation. So first I am going to use cosine ang and convert this cosine from -1 to 1 to 1.020 multiplied by the length, which is the less length. And for the y, minus sine ang, which is already a value from 0 to 1 because it's the angle is between 0 to pi. So the sine for the angle 0 to 180 degrees is always 0 to 1. So I don't need to do any fit function for this. Multiply by length, multiply by 0.5, and do some prim num function, prim num modular by 2 minus 0.5 times 2. Or in this case, this is gonna be always 0 because prim num is 0, so maybe I don't need this. So I could just skip this to -1, or I could just delete all these like this, make it a bit simple. Right? And that's for the left side primitive, but let's just try to visualize it how it looks like. So the new position is starting position plus a tangent vector times x times direction, which is a perpendicular direction, times y, which should create kind of an arc-like shape. And the reason why I make it half size of this cosine value is to not make the arc like a really arcy like shape, but make the height a little bit smaller, or maybe half size of the normal arc. So let's update the point. And let's see how it looks like. And Yeah, seems like it has changed. But it changed the right side. Oh, okay, so I needed to look from this side. And I guess it's correct, and I guess I was saying wrong here. The reason I made it 0.5 is to make the normal looking arc. Without it, I think it's gonna be a bit more larger. Yeah. So I needed 0.5 in order to make it like a normal arc size. Right. Okay, so let's do for the right side as well. So this was the left side. For the right side, I want to make an inner arc like this. So to do that, x equals to length time fit cosine angle minus 1 2 1 and 1 2 0 times length, and for this one I am going to multiply by 1.5 and subtract by 0.5. And maybe I should keep it like this and times length like this. Okay, for the y, I'm gonna say minus sine angle times length times 0.5, and in this case keep it as it is. Right, so for this one the x size is a bit bigger than the left one, and let's try to see the original line here. So it looks like this. So the left one have the same length as the original line for this arc, but the right one is a bit bigger, 1.5 times bigger, to make the shape a bit more interesting. So as you can see from the video capture, I'm trying to mimic the kind of essential shape of this single fin using these simple arc shape. Now having those lines, let's just do some Boolean again to have a Boolean union and Boolean difference to combine those curve together with the original shape, original donut-like shape. Alright, so first thing first, let's make those line a closed primitive, because currently it's just an open curve, so I am going to give a primitive node, click the face hole and close U to close straight. Right, now next I am going to split this geometry left and right, so I'm just gonna use a split node and split it to the 0. So left output will give you the left side arc, right input, right output will give you the right side output, right side arc. Now for the left output, I am going to combine it with the base fin, this one. So let's just do an object merge here, base fin. Let's bring up the base fin here and do a Boolean union, I guess, for this one. And so connect the base fin together with the left side arc and make it both surface. Then make the operation union. Right. Now, after that, I am going to give another Boolean here. This one and this one. And for this one, what I want to do is to do a subtract, so between surface and surface. So create something like this. Now it doesn't really look exactly like what I am showing here, but it's close enough. I'll keep it as it is. I'll keep it as this. Be the final shape. Now, I will say that this shape is good enough. What I want to do next is to... I don't like this seam line here, so let me see if I can delete this by using the divide node. By remove shared edges, and looks okay. Right. Now, next, since this is all flat now, but as a final shape, as a final fin shape, it has to be a part of a sphere. So in order to do that, I am going to use it as a guide to trim out from the sphere. So do a poly extrude for this one to make the distance high enough, maybe like 5, and also output the back so that it will become a solid geometry like this. And from here I want to trim out the base sphere with this guide. So bring up the sphere again, object merge, base sphere. Let's set it the color green and bring up the base sphere and do a intersection Boolean. So Boolean intersect with the extruded one, and the surface should be surface. I mean the sphere should be surface, and set the operation to intersect. And I got this and fin-like shape, one side of fin-like shape derived from the sphere, cut it from the sphere. Now that's good. The next thing I would like to do is since currently I have only one side, which if you see in the video captures, it's just the blue side, but I also want the pink side as well, and it's exactly the same shape, just connected at some angles on the center. So let's do that. I can do that by using two mirrors. So first have one mirror and set the mirror direction to y axis. And as you can see, there is a gap here, so I need to set the origin of the mirror, and that can be retrieved from the branch guide here. So if I click here, this is the point where the fin starts. So this can be the position where the mirror also starts for this shape. So, and if I look at the geometry spreadsheet of the branch guide, it only has one point, so I can refer to this one point from this branch guide. So let's do that. Let's go back to the mirror, to the origin of y. right expression point, branch, guide at 0, first point, and the point going to retrieve the point position and just look at the y value. Now I have successfully mirrored, but I still need to mirror it once again so that it will be facing the other way on the XZ direction. So let's do that. I'll give another mirror here and set it to also let's turn off the keep original check for both. Right, now that looks good. Now I guess I also wanna set the origin of the mirror here, derived from the radius of this sphere, I think. Let's try that out. So let's look at the detail. Radius, this one. And there was an attribute called radius to the first point. And nothing seems to change, so I guess it didn't really matter. That's fine. Wait, but if I change this value to my times 0.5, doesn't really change, so I'll just delete, make it empty, like 0. Alright, now next thing, what I would like to do is to rotate this mirrored fin, because right now it's touching a bit too much with the top one and the bottom one, so I wanna kind of offset this bottom fin to rotate it maybe to the clockwise direction to give a little bit more view space when how it touches. So let's do that, and I can do that by maybe setting some new parameters here called rotate, and I'll just set it integer. I'll call it rotate fin, maybe rotate fin. To make it parametric, and the value could be from 0 to 120 since the maximum angle of this fin is 120 degrees. Right, and just keep this value a bit random. Go back to the mirror here and connect new transform node. And to the y rotation value, relate pace relative. And as you can see, a bit of offset has been done. Now that's good. Now finally set some colors for both bottom and the top part with different colors, which I have already set it as a parameter here. So for the bottom part, I could use a magenta. Top part, I could use this blue one. So let's copy this blue one first. Copy parameter. Go back to the this one, which is the top part. I'll put the color node here and paste the color parameter for the top part. Let's copy this color parameter for the bottom, and let's change this color 1 to color 2 for R and RGB. Right, now finally merge these together. We'll have a fin, single fin looking like this. On the top side you have blue, on the back side you have magenta. Alright, now finally do some rotation in order to keep the center of this two fins, which is around here, to be the same position as this guide, which was a branch guide position. So right now the branch guide position is here, but I want to place this fin, center of this fin, to be the same position as this branch guide position point, since this place is gonna be the initial position where the fin comes. So let's rotate the fin, and I can do it procedurally based on the parameter that I have set before. So the value will be, I did the rotation here, and so what I could do is to come back to the parameter again, copy this rotate fin parameter, and go back. And for the Y rotation, I'll do a simple expression like this: 120 degrees minus paste relative reference rotate fin times 0.5. And that should, as a result, give you the center of this fin to be exact position as this guide position. Cool. Now that looks good. Now I have successfully set up the fin. What I just need to do now as a final setup is to place this thing on top of each moving branch tip point, and that is the most hardest but interesting part of this definition. Let's do that. Okay, we're almost there. Try to stick with me. So let's start by getting a branch guide again. So object merge, name it branch guide, and color this green. Look for the same name, branch guide, which is this one, the just 1 point as a reference. And also let's get the actual moving branch lines or structures. So that will be object merge branch sorry. Okay, these one, and these one is the actual branch lines which actually moves, depend on the move value, these one. But the branch guy is not going to move, it stays as it is. It's the initial position of the this guy, I think. So this will always stays as here, and also the fin that we have made also stays at the initial position here. So the goal here is to use both the initial branch guide point with three axis information, and up and forward, together with the fin at attached at this branch guide position. Then use those as a reference and transport it or orient this fin based on those 3 axes to a new 3 axis for each branches, which is this one, this one, this one, everything, a total of 12 branch points. So that's what I want to do. So in order to do that, I need to do some complex orientation calculations using some rotational matrix, and I'll show you how you can do that using those based on those 3 different axes as a guide. And that is a kind of a key point of this tutorial. All right. Now, first of all, from this branch, moving branch, I only need to get the branching point, the end tip point of this branch line. So let me just get that by connecting a delete node. Named branch, from points, delete non-selected. So now I've got 12 branch points, having 3 axes as showing as a plane. And let's do a for each loop for each points. So each loop I am getting 1 point here. Right, now this is the fun part. I am going to refer to the base guide axis points together with the fin points, and I'm going to orient this fin point from a source plane to a target plane, which is here, using some wrangle or vex function. And it's not really a simple vex function. There's no like plane to plane orientation in vex, unfortunately, so I had to make it by myself using a function called dihedral that we have used before, which is a vector to vector orientation. Alright, connect first input with the fin, second with the reference branch guide plane, and then third with the actual target plane. Then let's name this orient, and let's dive into the code. Alright, now let's first get the position of the source point. I'll name it source position 1 from the second input. Since there's only 1 point, I'll just pick the first point, 0. Position pos 2, this is the target position. Okay, and let's also give a direction from position 1 to position 2, which is a simple subtraction, like this. Okay, let's also get the normal vector from input 2, input 3. So norm 1 equals to point n 0, vector norm 2 point 2, and let's also get up from both input. The second one will be the source, and the third one will be target. So point 1 to 1 up, 0 vector up to point to up 0, and finally get the forward as well. Forward 1 point forward 0. Did I get the spell right? I hope so. And vector forward 2 point to forward, right? And what I'm as a goal, currently this fin is oriented on, placed on first of all at this position 1, and have a normal of normal 1 and up 1 and forward 1. What I want to do as a result is to change this fin position to position 2, as well as changing the normal to up 2, then forward to this forward 2 value. So I need to map all these information one by one to finally get the final orientated result, or rotation, final rotation, get the final rotation. So in order to do that, I can use a trick by calling multiple dihedral for every normal up and forward. So let's do that. First of all, let's create a first matrix, a rotation matrix, mat1, going from normal 1 to normal 2. So that can be written like this: from normal 1 using dihedral, normal 1 to normal 2. All right. Now, after getting it, let's give an angle between the forward 1 and forward 2 by calculating by using some trigonometry function called a cos, assign cos at, and using dot of forward 1 and forward 2, and also create a matrix R or matrix F named ident, and rotate this matrix by radians, almost 120 degrees, with the axis of normal 2. Now, here comes the part. Now, first of all, I am going to place the base point position to 0, 0, 0, so that I can rotate based on the 0, 0, 0 axis, or 0, 0, 0 position, which will be much easier to do. So first I'll move the point position to 0 by subtracting by position 1. Then rotate the point, each point, by matrix 1 that I have created here in order to map from normal 1 to normal 2. And do the same thing for the up vector. So up 1, multiply up 1 a matrix 1. So do the same rotation for the up one. And now give another matrix to calculate another dihedral, which goes from up 1, the rotated up 1 to a up 2 here. And do another rotation to a point with this mat 2. Starting to get it. Now, next is the forward time. So for the forward, I am going to forward 1 times mat 1. So that will be the first rotation here. Maybe I can just copy it, paste it here. And for the next step, I'm going to forward 1 multiply by newly created mat 2. And then create another matrix called mat 3 using dihedral, using updated forward 1 to a final forward 2. And use that matrix to update a point position again. And finally, set the point position to a position 2. And I think I didn't really needed this, probably. Let's remove this. And let's see how it goes. So this is the target position, and seems like the oriented fin is coming to the right position from what I see here. But let's see if I exit the loop, and voila, all the fins have seem to come to the right place based on the branch position plus the axis. And what if I change the move parameter here? Does it move along with it? Yes, it does. And success. Great. Yeah. And now it's pretty much all done. I just need to apply some, maybe a normal node here, group it with the network box, and give a null node, name it as fin, make it yellow color for this node, then cover all these with the one network node, and go back to the bottom part and add another object, merge, name it fin, color it green, refer to the fin, merge it, show everything, hide all these vector values, and connect with the new null node, name it as final, and let's see how it goes. So you have circle, plate, fins, and structures inside shown in red. Let's hide some seam lines. And if I change this move value, changing the structures from the blue to magenta, working really fine, working really good. And let's also try to change some parameters here. If I change the separate distance, if it make it close to 0, then all these offsetted value will become really small. You have those discs touching together. If you make it really big, you have really big gaps in between those discs. So I guess around 0.2 or something is good in terms of the visual. Then you could also change the hole size, which is the size of this disc, to small or big parametrically. And you can also control the gaps between the fins and the holes. And also you can control the rotation of the fin. And that's it. We have successfully created a switch pitch bowl kinetically moving and without using any physical structural simulations, also just by using geometrical calculations. And that is the kind of a point here. Awesome. Now let's just add some expression to animate this so that it will animate endlessly, and I will finish this video. Now let's go back. What's this point doing here? I'm not sure what this point is. If I go back to the geometry, I don't know, maybe it's some bug or something. Is it coming from fin? Maybe. Well, I'll just keep it as. I mean, maybe you can fuse it to remove this. If it doesn't remove, then I guess it's a bug with the preview. Doesn't really matter. Now, let's do some expressions. Go back to the controller, to the normal. So what I want to give is, based on the frame value, I want to go from open to close to open, and go seamlessly, happens continuously, infinitely. So I can use a sine function using a frame, and also I can fit this frame value. Since I know that the end value of this fin frame is 240, and I can get this value as an expression, so 0 to f end will become 0 to 360, which will be used as an angle for the sine. And so this will be from -1 to 1. Then I can fit this sine value from -1 to 1 to 0 to 1. And let's set the end value to something low, like 60. Set it to real time, and it will continuously move like the real switch pitch bowl. Voila. So that's it. This is how you can create a kinetic switch pitch bowl procedurally using Houdini. Thank you for listening. Thank you for watching this far. It has been a really long video again. I really appreciate people who made this far. Yeah. Thank you very much. And see you next time. Bye.